Well, it's not every day you get a piece of Canadian royalty on the bench, so I thought I'd better bring you guys in on this.
Canadian Prince now dipping his arms into the pudding, as is tradition.
I bought this off a friend of mine. I had a couple of issues with it. It kept blowing fuses and it had hum on the output. So I took it on. My little Samsung Servo 260 has been playing up for the last couple of months, so I was really excited to upgrade it with the Bryston. Lucky there are a lot of schematics for Bryston online, and it's all discreet. So I thought it's definitely worth a punt. My initial plan was to replace all the capacitors, and there were also some power resistors which had got really hot, so because I don't know the history of it, which is another story in itself, it was bought off eBay, and when my friend received it, one channel wasn't working, and then he took it to PMC. I think they just replaced the fuse and gave it back to him. And the hum situation was actually down to this backboard here. The mains comes into here, and via the switch as well, and the transformers connect to the board. There's a couple of LEDs on the front which connect there. These are actually occasionally were shorting out, so I put some heat shrink on there to stop that. I don't think that would have been causing the fuse blowing though. But the power scheme was completely plugged in wrong, and like the left earth was going to the right channel, and it was a mess. This page in the schematic really helped a lot. And they do an ingenious thing where they run the power transformers out of phase with each other, and so it looks like there's a bit of cross wiring. This is actually from an older 1980. I think this is 82, because the switching arrangement's a bit different, but it clearly shows you how like the live will come here, neutral there, and their inputs are phase reversed. Very clever. And the hum basically came from this earth going to the right channel and this earth going to the left channel. Classic ground loop. And they're actually not too bad to work on. It's a modular design, so we can pull each channel out. And there we're just left with the mains transformers and the filtering caps and the backboard, which connects to the phono inputs and the speaker outputs. This is the channel that I've already refurbished. I couldn't quite get hold of the actual caps that I wanted, so I've used these radial ones. There's enough space and clearance to use them, so there's no problem there. These resistors here I replaced. The wire rounds, I've replaced them with 2 watts, that's double their rating, and I've mounted them off the board. As you can see, the board has been discoloured due to the heat dissipation, so this amp has definitely seen some heavy action in the past. So a little Achilles heel of this amp, and something to bear in mind, is this preset potentiometer here. It's used to set the biasing for the transistors, and as you can see, it's an open carbon track. Dust can fall in there, and if this trimmer goes open circuit when you turn it, then it will drive the transistors really hard, which you don't want. So if you're working on one of these, I would definitely look at this pot first before you do anything. There's a little poly put the kettle on capacitor here. I think it's about 7N8. I touched that with my soldering iron when I was fixing it, so it made it go short, so I ended up having to replace it, and I just put a modern ceramic one in there and it seems to be okay. And I replaced the bias trim pot with this multi-turn one here, which is not strictly necessary, but it's actually good to change the bias settings really slowly. The first thing we got to do here is take these PCBs out. And to do that we have to remove all these power transistors. The right way round. This is the PNP section and this is the NPN section. And interestingly for us Brits, the Canadians seem to use this square driver, which was a bit odd at first, but in actual fact it's way better than any Phillips or slot head thing. Okay, that lot's out. I labelled them up as to where they came from. They use parallel transistors, so they need to be matched. I could quite easily sell them on eBay. This is from a working channel. I'm using these MJ21194, which is matched with its 9.3 counterpart. I believe, someone correct me if I'm wrong, that these are what's used in the new 7Bs. Anyhow, yeah, you can see these have got numbers on them as well when I put them through the matching process. I ended up spending about an extra £30 for extra ones to make the matching process go a bit easier. So I have a couple spare now. Okay, so what we're left with, we still have the Mikas on here for the heat sinks. If they're in good condition, you can just clean them. I've had transistors in and out during the matching process that I've actually got all new set of these, so I don't need to keep these. Although I can't bring myself to throw them away, let me put them somewhere. Right, so, don't know if you can see, can I show you this? You'll see it in a minute, but these screws holding in these sockets to the board are the same screws that hold the transistors in, and there's still 4 more screws which hold the board in. Okay, you can see we've got the board out now. It connects into this edge connector. At first I thought that was loose, but it's designed like that so you don't get any mechanical stress on the corner joins. There is one transistor here which connects to this edge board, and that confused me for a little while because when I was trying to match the transistors on here for the different versions, I found one that was the most closest, but there seemed to be one more transistor, and eventually I found it. It was under the board. This thing here, I think it's just a temperature sense to sense how hot things are getting. This needs a whole clean out. It's absolutely disgusting. I've got heatsink compound on my hands which is toxic, so before I do anything with this, I'm going to just give this a really good clean and clean off all the old heatsink compound. There we go, like new old stock. And now it's time to look really up the queen skirt. So here you can see the flux residue left over from the manufacturing process. Now I can't really stand that, so I'm going to have to clean it all off. Okay, I've got all that cleaned up. It looks much nicer now. Be careful with any heatsink compound that's got into these holes. You don't want to push the heatsink compound down even further. I've cleaned up this side as well. Okay, so the next step is to just replace these capacitors. I'm going to leave the power resistors because they don't look as bad as the old ones. I had to replace a couple on the other board. These went out of spec and you can see how hot they must have got in the past. I'm going to leave the tantalums in. I don't know whether that's going to be a bad move. Okay, that's all back in. We got the preset pot caps changed. Looking good. I've secured these PCBs in with there's four bolts. They actually attach to this top socket here, and that holds it all in place. So here's our first pair of match transistors that got to go in. And I use this old brush, which I've chopped it off to make it a bit more stiffer. And then we take the mica and you can press it down to make sure there's no air gaps. And then we do that again. And then always give the legs a wipe, make sure we don't have any heatsink compound left on the legs, because it's not conductive. Okay, I'll put the first screw in, but I don't tighten it, and then get the other screw in. And then that's just very ever so slightly tight, and then I'll evenly spread the pressure. There we go. Okay, so I'll do the others. So everything's in there now. So for our first sanity check, I'm going to run it off my bench power supply. We're going to start off at plus and minus 5 volts. The minus 5 volts is here, plus 5 volts is here, and this is the ground. A signal I'm bringing in for my key flea, and we are scoping the input there. And then this white cable is the speaker output, which is going to this 8 ohm 500 watt load, and the other side goes back to earth. This is the bench power supply we're going to use. It can go up to 30 volt 2 amps. I've capped off the power supply to about 600 milliamps to start off. Let's turn it on. So we have plus 5 volts in and out, and we can see on the scope we have an output, which is a good sign. If I remove the input trace, you can see it's distorted, but that's because we're well under power. Bear in mind I've set the bias trim pot to the minimum amount, and we're only drawing a total of about 16 milliamps. Okay, so let's ramp up some voltage. Let's put the input back. And we can see that we're 128 millivolts peak to peak and 3.4 volts output, so still a substantial amount of gain. Okay, let's wind her up a bit. Let's go to 10 volts. At 10 volts, we can see the distortion is gone. Looking very good. And considering the bias isn't set, and we're running at about 25 milliamps, so we're going to increase the voltage. Let's go to 20 volts. I'm keeping an eye on the current draw. We're now at 20 volts, and we're drawing about 75 milliamps. Let's go to 30 volts. The power supply in the Bryston is actually running at plus or minus 80 volts, so we're not even halfway there. Oh. And you can see how the signal doesn't really react to an imbalanced power supply. It's kind of immune to the voltage rails, really. It's quite amazing. Okay, well, we're at 30 volts. Let's increase the input because we're only at 128 millivolts. Let's take that up to 8. This one is the input, this is the output. Still don't see any crossover distortion. Interesting. And now we're coming in at 464 millivolt peak to peak, and the output is now 15 volt peak to peak. Let's take it higher. Okay, we're drawing about 100 milliamps now. Everything looks really good. Yeah, I think this is the safest way to try and reboot one of these Brystons. We can guarantee not to blow anything up. Okay, so before we give it full mains voltage, I'm going to run it through my little limiter here. Basically, the mains comes in here. The neutral and the earth goes to the socket, but the live goes via in series with this incandescent light bulb. And the idea is if there's any shorts, this will light up and soak up a lot of current, so nothing should get damaged. And when we turn it on, you'll see it flash bright as the capacitors charge, hopefully. And we've still got the dummy load connected. Okay, brilliant. And we have a signal. Let's just give it a bit more amplitude. Let's double it. Okay, great. I think that's going to be good. So the next stage is full 240 volts. Okay, she's plugged in straight into the mains. Pulling 97 watts. That does die down. Okay, I'm going to plug the other side back in now. We're only going to be looking at the right hand channel for now. The left hand channel's fuse has been taken out. I'm injecting a 20 kilohertz sine wave at 1 volt RMS on the input. And I'll turn it on. So 60 volt peak to peak coming out. Let's get rid of the little bit of a phase shift there. And there you can see the kink in the crossover distortion. Now I'm just going to short the input. Just got a little phono where I shorted out the end. So we measure at the test point. Okay, and we slowly turn it up. And eventually it will start conducting. Okay, it started conducting now. That's at 1 millivolt. I just want to see how much kink there is at 1 millivolt. Don't know if you can see that on the scope. There's still a slight kink there. So I'll put the short the input again. Okay, that's at 2 millivolts. That's only halfway there. But I'm just interested to see what happens to the signal input. Difficult to see on the scope, but definitely I think there's a little kink there. We're at 36 watts. Okay, that's 3 millivolts. That's 39 watts. So increasing the bias increases the whole current draw. So that's at 3 millivolts. That looks good to me. Now we're pulling 325 watts with this situation, and that's getting quite warm. So I did the same thing on the left channel. I set the bias up at 3 millivolts. No distortion on the sine wave. I've just hooked it up to the spectrum analyzer in transfer function mode so we can see the frequency response. And as you can see, that is just flat. You can't really ask more than that. That's up to 25 kilohertz. It's the next day now, and this has been on test pretty much constant. I've been doing so much listening. Definitely an improvement over the Samson. And interestingly, today, after just remeasuring the bias voltages, they were both at 4.1. So that was quite interesting. But I hope you enjoyed that, and I'll see you next time.